I call it advanced because it's a difficult computation actually. I call it, it's a question 2 again, part B. I call it plus plus because actually it's not part of that question in the yellow book, what we're going to discuss, but the data, the actual linear map, is taken from that question. So if you remember, there was a map like that there. It was a map which take R4 into R3. Here was the formula for that map. I'm just repeating this stuff from 2 slides ago. No, from 3 slides ago. And next is a 4-component vector like so. Okie dokie. So in that, when we first approached this question, we did what the question actually asked. We found the metrics of this linear transformation. So we found the metric with respect to the standard basis. Now I'm going to alter the basis again. I'm going to take another basis and I will come up with the metrics with respect to this new basis. So here's my new basis. U1, it's the vector like this. So it's first to 1, 1, 0, 0, and we have some scaling in front. U2, again, some scaling. And 1, negative 1, 0, 0. U3, again, some scaling. And 0, 0, 1, 1. And U4 is a vector like this. Scaling 0, 0, 1, negative 1. These 4 vectors, they come from here, from R4. I claim this will be a basis. Why it will be the basis? Can you just tell me? I mean, can you just, anyone has any bright ideas why this could be a basis? Thank you very much. These vectors are orthonormal. I'm not going to check it right here, but I'll leave the check for you. This B, the set B composed out of these vectors is orthonormal system, meaning that they're all unital. If you compute the lengths of those vectors, it will be 1 all the time. All of them unital, all 4. And also, they are pairwise orthogonal. If you compute the dot product of uj and uk, as long as j not equal k, that will be 0. We proved this in class together with you, that orthonormal system is always linearly independent. That's why, because of that result, this is basis in R4. So I just try to find the metrics of my linear transformation with respect to this basis. Yeah. If I need to do something like this, my approach or the method starts with computing action of t on each of the vectors of my basis. So t of u1, I have to take these components and I have to plug them in this expression. Let's just see if I did my arithmetic right yesterday. This is just because of the linearity, we can keep the scale in front. That's what I'm doing. And when I sub in my 1, 1, 0, 0, it will be negative 2. This is 0. 6 take 8, it's another negative 2, right? Because 1 and 1. And here negative 2 plus 4, it's plus 2. Here's my result. T of u2. Again, scaling because of linearity, we just keep it in front. If I sub in 1 and negative 1 in here, it will be negative 2. 6 plus 8, it's 14. Negative 2, 14. And here will be negative 2 and negative 4, it's negative 6. Here's my action. T of u3. Now I sub in this vector, again scaling, because of the linearity comes like this. First component is 5, let's just double check that. Yes, it is. Second component is these two 0, and it will be 2. And the last component is negative 3. And T of u4, here's my scaling from here. When I sub in these components, it will be 5. Negative 2 and negative 3 again. That's all the values for my t. If I pick now the standard basis in the codomain, if I pick C to be standard basis in here, we can now identify the matrix of my transformation with respect to this pair of bases. This and this is the matrix. The matrix of my transformation with respect to the pair B and C, it's simply these vectors taken as columns. Because all of these vectors, they share the same common factor, I just put this factor in front of my matrix, and the rest will be just the columns, like so. So the first row, -2, -2, 5, and 5. Second row is -2, 14, 2, and -2. And the last one is 2, -6, -3, and 3 is my matrix. This is not over yet. I will step up now the equation even further. So this content, it was the first plus in this name. Now I have some content for the second plus. That's why it's double plus. I'll take a non-trivial basis in codomain as well. And that's my non-trivial basis. For that I need to pull it, I need to bring this up a little bit. This one, not really, because the, yes, actually it should be. Thank you. Yeah, that's right. Thank you. It should be negative. I'll just fix everything across. Anyway, now what I'm going to do for the rest of the slide is this. I'm going to take another basis in R3. Here's my new basis. I will call it W1. Again, it's a scaling. 1, 1, 0. W2. It's a scaling. 1, -1, 0. And W3, 0, 0, 1. If I take this 3 as the set, and I will call this set G, this is another example of the orthonormal system. And that's why it is another basis in R3 now. So that's another basis in the codomain, and it's legitimate to ask what will be the matrix of my T if I replace this standard basis here with this new set G. Well, like it or not, we have to follow the same tracks we just followed on the slide before. I need to take my values, T of U1, T of U2, T of U3, T of U4, and I have to represent them as a linear combination of W1, W2, and W3. So I need to find these unknowns. Yeah, I don't need all of that. These unknowns. I have to take T of U1, and I have to find the coefficients, unknown coefficients, which give me a representation of T of U1 as a combination of W1, W2, and W3. Pay attention to indexing I'm using. It's the same idea behind the indexing as from the slide before. T of U2, T of U3, all of these unknowns components, then we have to find them, and T of U4. When we find them, we will take these unknowns as columns of this matrix we're looking for, with G replacing C in here. At this stage, our approach will just go a different way. I mean, from the slide before, I'm not going to take the augmented matrices for each of these equations, even though you may do that if you wish, but it's a quite difficult with the numbers like so. Instead, we're going to use another fact, another positive, very, very effective way of solving things when you deal with orthonormal systems. I don't know if you remember that, with something like this we discussed with you, and that's the main advantage of having orthonormal system. It says this: if you have a vector in R3, and if you're interested in finding these coefficients, lambda 1, lambda 2, lambda 3, giving the representation of this vector in terms of W1, W2, W3, you don't have to, in general, of course, you have to solve for that system of linear equations, 3 unknowns, 3 equations. But when you look at the orthonormal system, you don't have to do that. There is a direct formula for each of these unknowns. Do you remember the formula? Each of these lambda j's, you can recover them by taking the dot product of the left-hand side, or in the official language, it should be the right-hand side of my equations, with the individual elements of your orthonormal system. 1, 2, 3. So when I will be looking for these coefficients, I'm not going to solve for any augmented matrices. I will be just computing dot products. It will be 12 different dot products we will need to compute, right? Because we have 12 unknown coefficients. But this is still easier than solving the augmented system. I intentionally gave you this question with this many unknowns to once again show you how great it is to deal with the orthonormal systems. So let's just do that. What do I do? I need to find these coefficients. To find these coefficients, I have to take this vector, t of u1, and I have to dot product this vector with each of my w1, w2, w3. My t vectors, they stayed a little bit up, a little bit towards the top of my slide, but actually I can take them from this matrix, right? That's why, or maybe I can scroll it down a little bit, can I? Let's just scroll it down a little bit. Oh, all of them. Every information we need to finish my evaluations, it's present now. Let's just try to do that. What will be the dot product of this vector and w1? That's my vector, and that's w1. We can do it from the top of our heads. Common coefficients 1 root 2, 1 root 2 will give me just 1/2. And the dot product of these two will be negative 2, negative 2, 1, and 1. It's negative 4. So altogether just 2. 2 w1. Dot product of these two vectors of t of u1 and this w2, because of the negative here, it will be negative 2 plus 2. So it is 0. And now the dot product of my t of u1 with the last vector, w3, it's simply 2 by root 2. Here's my unknown coefficients. If something is wrong. You see, I'm now looking at you because you see you're so good in following what I'm saying and finding the typos there. Anyway, t of u2. I take this vector, t of u2, this one, and I dot product one after the other with each of the w's. We can do it from the top of my head again. Common coefficient here gives me 1/2, and here will be negative 2 plus 14, which makes it plus 12. By 1/2, it's 6. Second one, it's negative 2, negative 14, right? Because it's negative 1 here. So it's negative 16. By 2, it's negative 8. And the last one is it's just 1 inch here. So it's negative 6 by root 2. It's negative 3 root 2. 6 coefficients at an instant we just found. Only because we're looking at the orthonormal system. Now here, t of u3, here it is, dot product with w1. It will be 5 plus 2, which is 7 by root 2. Or by 2 actually, because it's root 2 squared. So it's the coefficient next to w1. If I dot product this vector with the w2, it will be 5 take 2 because of the negative. So it will be 3 on 2 w2. And the final one will be negative 3 by root 2. Well, the final step is t of u4, which is here. And again, I have to do the dot product. And I will do that. It's doable, and why not to do it? So it will be 5 take 2. And there will be a typo actually, because you fixed the typo, and my computation actually relied on the wrong value here. So we'll need to fix that as well. So it will be 5 take 2. It will be 3 on 2. Oh, that's another typo because it's a root 2 and root 2. It's a typo. It should be 2 here rather than root 2. I'll fix that. W1, second component because of the negative here, the 5 plus 2. It's another typo which needs fixing, and there will be a third typo. Yeah, it will be a third typo. So lots of typos to fix in this. Two here. 2 here, and negative in here. Here's my coefficients. If I can now collect all of these coefficients as columns in my matrix, here will be the matrix of my T with respect to the bases B and G. 2, 6, 7, half, 3. This needs fixing. 2, 6, 7 on 2, 3 on 2. Second row, it's a second set of coefficients, 0, negative 8, negative 3 halves, and this needs fixing. And the last one, root 2, negative 3 root 2, negative 3 on root 2, and this needs fixing as well. So we just fix that. Here's my fix for this component. Here's my fix for this component. And here's my fix for this component. Yeah, believe it or not, this is the correct matrix now, hopefully.